Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ernest Rutherford's 1919 paper, An Anomalous Effect in Nitrogen, marks a pivotal moment in the history of nuclear physics, a culmination of years of meticulous experimentation and profound insight into the structure of the atom. Its significance extends far beyond its immediate findings, laying the groundwork for the discovery of the proton and ushering in the era of artificial transmutation. This essay will delve into the historical context, experimental details, intellectual contribution, and lasting legacy of this seminal. The genesis of Rutherford's experiment could be traced back to his groundbreaking work on radioactivity and atomic structure in the early 20th century. Preceding 1919, Rutherford had already established himself as a leading figure in physics. His gold foil experiment in 1911, conducted with Hans Geiger and Ernest Marston, revolutionized the understanding of the atom. This experiment demonstrated that the atom consisted of a tiny, positively charged nucleus surrounded by orbiting electrons, a model that supplanted the previously held plum pudding model proposed by J.J. Thomson. The scattering of alpha particles by the gold foil provided empirical evidence for the existence of a concentrated positive charge within the atom. Following this discovery, Rutherford dedicated his research to exploring the nature of the nucleus itself. He and his team bombarded various gases with alpha particles emitted from radioactive sources, observing the resulting interactions. These experiments, performed painstakingly over several years, revealed the potential for transforming one element into another, a process known as artificial transmutation. Rutherford's earlier work with hydrogen had suggested that alpha particles could eject hydrogen nuclei from certain materials. These hydrogen nuclei, which Rutherford later named protons, appeared to possess surprisingly high energy and range compared to the incident alpha particles. The 1919 paper specifically addresses the anomalous behavior observed when alpha particles were passed through nitrogen gas. Rutherford noticed that when nitrogen was bombarded with alpha particles, scintillations, or flashes of light, were observed on a zinc sulfide screen placed beyond the gas chamber. These scintillations indicated the presence of particles with a range significantly greater than that of the alpha particles themselves. Crucially, these long-range particles were present even when the alpha particles were completely absorbed by the nitrogen gas. To ascertain the nature of these long-range particles, Rutherford conducted a series of experiments. He carefully controlled the purity of the nitrogen gas to eliminate the possibility of contamination from other elements, like hydrogen. He also varied the energy of the alpha particles and the pressure of the gas to study the relationship between these parameters and the number of long-range particles produced. In addition, he performed control experiments using oxygen and carbon dioxide, where the effect was minimal. His observations led him to conclude that these long-range particles were due to alpha particles themselves. Any other known contaminant or were rather a product of an interaction between the alpha particles and the nitrogen Rutherford hypothesized that the alpha particles were somehow disrupting the nitrogen nucleus, causing it to eject a hydrogen nucleus, or proton. This was a revolutionary idea, as it implied that the nucleus was not an indivisible entity, but rather a composite structure containing smaller constituents. The transformation he proposed was nitrogen plus alpha particle yields oxygen plus proton, symbolically written as nitrogen-14, 7 plus helium-4, 2 yields oxygen-17, 8 plus proton-1. The experimental setup employed by Rutherford involved several key components. An alpha particle source, typically radium or one of its decay products, emitted alpha particles into a chamber filled with the gas being studied. The chamber was equipped with thin windows that allowed the alpha particles to enter and the resulting particles to exit. A zinc sulfide screen, placed outside the chamber, was used to detect the particles. When a charged particle struck the screen, it produced a tiny flash of light, or scintillation, which could be observed through a microscope. The distance between the gas chamber and the screen could be adjusted to measure the range of the particles. Rutherford and his assistants, primarily assistants due to his administrative role at the Cavendish laboratory following J.J. Thomson's departure, painstakingly counted these scintillations over long periods, meticulously recording the day. The immediate impact of Rutherford's discovery lay in its demonstration of artificial transmutation. He had shown that it was possible to alter the nucleus of an atom, effectively changing one element into another. This discovery shattered the long-held belief in the immutability of elements, a cornerstone of classical chemistry. Furthermore, the identification of the proton as a fundamental constituent of the nucleus opened up new avenues of research into the structure of matter. Rutherford's work provided a crucial step towards understanding the composition of atomic nuclei and the forces that hold them together. Rutherford's discovery, while revolutionary, was not without its critics. Some scientists questioned the interpretation of the experimental results, suggesting alternative explanations for the observed scintillations. For instance, the presence of trace amounts of hydrogen as a contaminant was a persistent concern. However, Rutherford's meticulous experimental design and careful control experiments addressed these concerns, bolstering the validity of his conclusions. One of the most significant challenges in interpreting Rutherford's results stemmed from the limited understanding of nuclear forces at the time. The strong nuclear force, which binds protons and neutrons together in the nucleus, was yet to be discovered. Without this understanding, the nature of the interaction between the alpha particle and the nitrogen nucleus remained a mystery. The concept that the alpha particle had sufficient energy to overcome the repulsive electromagnetic force between the positively charged alpha particle and the nitrogen nucleus also posed a challenge for scientists at the time. The importance of Rutherford's experiment extends far beyond its immediate impact. His discovery of artificial transmutation paved the way for the development of particle accelerators, which have become essential tools in modern nuclear and particle physics. These accelerators allow scientists to bombard atoms with particles at much higher energies than those achievable with radioactive sources. These higher energies facilitate the creation of new elements and the study of fundamental particles. The discovery of the neutron in 1932 by James Chadwick, a former student of Rutherford, further solidified the understanding of the nucleus. Chadwick's experiment, which involved bombarding beryllium with alpha particles, revealed the existence of a neutral particle with a mass similar to that of the proton. With the discovery of the neutron, the nucleus was understood to be composed of protons and neutrons, collectively known as nucleons. This model, elaborated through the work of Werner Heisenberg and others, provided a comprehensive explanation for the properties of atomic nuclei and for nuclear reactions. Rutherford's 1919 paper also profoundly influenced the development of nuclear medicine. Radioactive isotopes, produced through artificial transmutation, have become invaluable tools in medical diagnosis and treatment. For example, radioactive iodine is used to diagnose and treat thyroid disorders, while radioactive isotopes of cobalt are used in radiation therapy to treat cancer. These applications of nuclear physics can trace their roots back to Rutherford's pioneering work. The legacy of Rutherford's 1919 experiment continues to resonate in contemporary physics. Modern research in nuclear physics builds upon the foundations laid by Rutherford, exploring the fundamental forces that govern the behavior of matter at the subatomic level. Scientists continue to probe the structure of nuclei, seeking to understand the properties of exotic nuclei and the nature of nuclear matter under extreme conditions. The discovery of induced or artificial radioactivity by Ion, Joliot-Curie, and Frédéric Joliot in 1934 was directly inspired by Rutherford's work. They demonstrated that stable elements could be made radioactive by bombarding them with alpha particles. This discovery opened up a vast new field of research in nuclear chemistry and medicine. Radioactive isotopes could be produced in large quantities using particle accelerators and nuclear reactors. A subtle, yet profound, implication of Rutherford's work was its challenge to the alchemical dream of transmuting base metals into gold. While Rutherford's experiments did involve the transmutation of elements, the transmutation occurred at the atomic level. With the creation of new radioactive isotopes, the alchemical ideal of transmuting common metals, such as lead, into precious gold remained elusive. However, it is a curious historical irony that Rutherford, improving the possibility of transmutation, albeit in a far more nuanced way, had effectively laid the groundwork for the eventual, if impractical, technological realization of the alchemist's aspirations. Critiques of Rutherford's initial interpretation arose from discrepancies in energy balance within the proposed transmutation reaction. The kinetic energy of the emitted proton appeared to exceed what could be accounted for solely by the energy of the incident alpha particle. This discrepancy was initially perplexing, requiring a deeper understanding of nuclear binding energy and the role of the strong nuclear force. Later refinement of nuclear models and the precise measurement of nuclear masses resolved the energy imbalance, reaffirming Rutherford's experimental observation while demanding a more sophisticated theoretical framework. The conceptual leap made by Rutherford was considerable. He moved beyond the idea of the atom as a simple, indivisible building block to envisioning the nucleus as a complex structure capable of being transformed. This intellectual transition was crucial in driving forward the field of nuclear physics. It spurred further research into the constituents of the nucleus and the forces that govern their interactions. In conclusion, Ernest Rutherford's An Anomalous Effect in Nitrogen is a landmark paper that inaugurated the field of artificial transmutation and revealed the composite nature of the atomic nucleus. His meticulous experimentation, insightful interpretation, and bold hypothesis led to the discovery of the proton and opened up new horizons in nuclear physics. The paper's direct applications extend to particle accelerators, nuclear medicine, and fundamental particle physics. The legacy of this work continues to inspire and inform scientific inquiry into the structure of matter and the nature of the universe. Rutherford crafted a seminal work, altering the course of physics and forever changing our view of the atom.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.